So now that we understand what a secure PRG is, and we understand what semantic security means, we can actually argue that a stream cipher with a secure PRG is in fact semantically secure. So that's our goal for this segment. It's a fairly straightforward proof, and we'll see how it goes. So the theorem we want to prove is that basically given a generator G that happens to be a secure pseudorandom generator, in fact the stream cipher that's derived from this generator is going to be semantically secure. Okay, and I want to emphasize that there was no hope of proving a theorem like this for perfect secrecy, for Shannon's concept of perfect secrecy, because we know that a stream cipher cannot be perfectly secure because it has short keys. And perfect secrecy requires keys to be as long as the message. So this is really kind of the first example that we see where we're able to prove that a cipher with short keys has security. The concept of security is semantic security, and this actually validates that really this is a very useful concept. And in fact, we'll be using semantic security many, many times throughout the course. Okay, so how do we prove a theorem like this? What we're actually going to be doing is we're going to be proving the contrapositive. What we're going to show is the following. We're going to prove this statement down here, but let me parse it for you. Suppose you give me a semantic security adversary A. What we'll do is we'll build PRG adversary B that satisfies this inequality here. Now, why is this inequality useful? Basically, what do we know? We know that if B is an efficient adversary, then we know that since G is a secure generator, we know that this advantage is negligible, right? A secure generator has a negligible advantage against any efficient statistical test. So the right-hand side basically is going to be negligible, but because the right-hand side is negligible, we can deduce that the left-hand side is negligible, and therefore the adversary that you looked at actually has negligible advantage in attacking the stream cipher E. Okay, so this is how this will work. Basically, all we have to do is given an adversary A, we're going to build an adversary B. We know that B has negligible advantage against the generator, but that implies that A has negligible advantage against the stream cipher. Okay, so let's do that. So all we have to do again is given A, we have to build B. So let A be a semantic security adversary against the stream cipher. So let me remind you what that means. Basically, there's this challenger. The challenger starts off by choosing a key K, and then the adversary is going to output two messages, two equal length messages, and he's going to receive the encryption of M0 or M1, and then he outputs B prime. Okay, that's what a semantic security adversary is going to do. So now we're going to start playing games with this adversary, and that's how we're going to prove our lemma. All right, so the first thing we're going to do is we're going to make the challenger also choose a random R, okay, a random string R. So, well, the adversary doesn't really care what the challenger does internally. The challenger never uses R, so this doesn't affect the adversary's advantage at all. The adversary just doesn't care that the challenger also picks R. But now comes the trick. What we're going to do is instead of encrypting using GK, we're going to encrypt using R. And you can see kind of basically what we're doing here. Essentially, we're changing the challenger, so now the challenge ciphertext is encrypted using a truly random pad as opposed to the pseudo-random pad GK. Okay, now the property of the pseudo-random generator is that its output is indistinguishable from truly random. So because the PRG is secure, the adversary can't tell that we made this change. The adversary can't tell that we switched from a pseudo-random string to a truly random string. Again, because the generator is secure. Well, but now look at the game that we ended up with. So the adversary's advantage couldn't have changed by much because he can't tell the difference. But now look at the game that we ended up with. Now this game is truly a one-time pad game. This is a semantic security game against the one-time pad because now the adversary is getting a one-time pad encryption of M0 or M1. But in the one-time pad, we know that the adversary's advantage is 0 because you can't beat the one-time pad. The one-time pad is secure, unconditionally secure. And as a result, because of this, essentially, since the adversary couldn't have told the difference when we moved from pseudo-random to random, but he couldn't win the random game, that also means that he couldn't win the pseudo-random game. And as a result, the stream cipher, the original stream cipher, must be secure. So that's the intuition for how the proof is going to go. But I want to do it rigorously once. From now on, we're just going to argue by playing games with a challenger, and we won't be doing things as formal as I'm going to do next. But I want to do formally and precisely once, just so that you see how these proofs actually work. Okay, so I'm going to have to introduce some notation. And I'll do the usual notation. Basically, in the original semantic security game, when we're actually using a pseudo-random pad, I'm going to use W0 and W1 to denote the event that the adversary outputs 1 when he gets the encryption of M0 or gets the encryption of M1 respectively. Okay, so W0 corresponds to outputting 1 when receiving the encryption of M0, and W1 corresponds to outputting 1 when receiving the encryption of M1. So that's as in the standard definition of semantic security. Now, once we flipped to the random pad, I'm going to use R0 and R1 to denote the event that the adversary outputs 1 when receiving the one-time pad encryption of M0 or the one-time pad encryption of M1. So we have 4 events, W0, W1 from the original semantic security game, and R0 and R1 from the semantic security game once we switched over to the one-time pad. So now let's look at relations between these variables. So first of all, R0 and R1 are basically events from a semantic security game against a one-time pad. So the difference between these probabilities is, as we said, is basically the advantage of algorithm A, of adversary A, against the one-time pad, which we know is 0. Okay, so that's great. So that basically means that probability of R0 is equal to the probability of R1. So now let's put these events on a line segment between 0 and 1. So here are the events, W0 and W1 are the events we're interested in. We want to show that these two are close. Okay? And the way we're going to do it is basically by showing, and here is probability R0 and R1, and since they're both the same, I just put them in the same place. What we're going to do is we're going to show that both W0 and W1 are actually close to the probability of RB, and as a result, they must be close to one another. Okay, so the way we do that is using a second claim. So now we're interested in the distance between probability of WIB and probability of RB. Okay, so we'll prove the claim in a second. Let me just state the claim. The claim says that there exists an adversary B such that the difference between these two probabilities is basically the advantage of B against the generator G. And this is for both B's. Okay, so given these two claims, the theorem is done because basically, what do we know? We know that this distance is now less than the advantage of B against G. That's from claim 2. And similarly, this distance is less, actually it's even equal to, I don't have to say less, it's equal to the advantage of B against G. And as a result, you can see that the distance between W0 and W1 is basically at most twice the advantage of B against G. That's basically the theorem we were trying to prove. Okay, so the only thing that remains is just proving this claim 2. And if you think about what claim 2 says, it basically captures the question of what happens in experiment 0, what happens when we replace the pseudo-random pad GK by a truly random pad R, right? Here in experiment 0, say, we're using a pseudo-random pad, and here in experiment 0, we're using a truly random pad. And we're asking, can the adversary tell the difference between these two? And we want to argue that he cannot because the generator is secure. Okay, so here's what we're going to do. So let's prove claim 2. So we want to argue that in fact there is a PRG adversary B that has exactly the difference of the two probabilities as its advantage. Okay, and since the point is, since this is negligible, and that's basically what we wanted to prove. Okay, so let's look at the statistical test B. So what is statistical test B? It's going to use adversary A in its belly, so we get to build statistical test B however we want. As we said, it's going to use adversary A inside of it for its operation, and it's a regular statistical test. So it takes an n-bit string as input, and it's supposed to output, random or not random, 0 or 1. Okay, so let's see. So first thing it's going to do is it's going to run adversary A, and adversary A is going to output 2 messages, M0 and M1. And then what adversary B is going to do is basically going to respond with M0 XOR the string that it was given as input. All right, that's the statistical test. And then whatever A outputs, it's going to output as its output. And now let's look at its advantage. So what can we say about the advantage of this statistical test against the generator? Well, so by definition, it's the probability that if we choose a truly random string, so here R is in 0, 1 to the n, it's the probability that B outputs 1, minus the probability that when we choose a pseudo-random string, B outputs 1. Okay? Okay, but let's think about what this is. So what can you tell me about the first expression? So what can you tell me about this expression over here? Well, by definition, that's exactly, if you think about what's going on here, this is exactly the probability R0, right? Because this game that we're playing with the adversary here is basically he outputs M0, M1, right? Here he outputted M0, M1, and he got the encryption of M0 under a truly one-time pad. Okay, so this is basically a probability of R0. Here, let me write this a little better. So this is basically a probability of R0. Now, what can we say about the next expression? Well, what can we say about what happens when B is given a pseudo-random string Y as input? Well, in that case, this is exactly experiment 0 in the true stream cipher game, because now we're computing M XOR M0 XOR GK. So this is exactly W0. Okay, that's exactly what we had to prove. So it's a kind of a trivial proof. Okay, so that completes the proof of claim 2. And again, just to make sure this is all clear, once we have claim 2, we know that W0 must be close to W1, and that's the theorem. That's what we had to prove. Okay, so now we've established that a stream cipher is in fact semantically secure, assuming that the PRG is secure.